working through a number of We're going to work through a number of scenarios in the rental car industry here. So I'm just going to go over a brief agenda here. So again, as I mentioned, we're going to get a 30,000 foot view of revenue management and kind of see what is this discipline all about. Again, I find that this is something that tends to be less encountered compared to some of the other applications, the other major applications of operations research. And this is really an interesting area. Really actually aligns a number of different types of analytics together to really bring real value to businesses. So I'm going to spend a little bit of time talking about, what is revenue management in general, and then we're going to move on to a series of scenarios here. So we're going to start with a very simple scenario, again, looking at the rental car business. One of the things we're going to see is that when we talk about revenue management, the way we apply there's some general principles that you find and some general components that you'll find across industries, but the way that they're put together and the way that they're applied to the industry, it varies greatly from one industry to another. Every industry has some of its unique features and requires a unique tailored approach to apply revenue management. So within the rental car industry, we're going to talk a little bit about some of the features that characterize this particular industry. And we're going to work through a series of exercises together through scenarios where we start off with a very simple scenario where we have a single rental car location. So maybe a small, single town rental car business. And then we're going to see how we apply revenue management in that context. And then we're going to extend it to more realistic cases where we have multiple locations. We'll transition to a multi-location, a simplified version of a multi-location rental car business, applying revenue management to that. Then we'll add some realism in terms of how we transfer cars from one location to another. And then finally, we're going to see how we can adapt the models that we have to incorporate dynamic pricing and fluctuating demand. And then I want to end with a short discussion on the ethical use of revenue management. Again, when we talk about doing things like dynamic pricing, charging different prices to one customer segment versus another, there's some ethical issues that you should be aware of, and just want to be mindful as you look to possibly apply this in a real context. And then we'll take some time towards the end and have questions and discussion. So as we get started, I'll just give a brief introduction of myself. My name is Chris Garcia, and I am a professor of quantitative methods here at the University of Mary Washington, located in Fredericksburg, Virginia. And this is on the East Coast, right in the middle of the East Coast in the U.S. In my work at Mary Washington, I teach courses in data science and operations research at the graduate and undergraduate level. My research focuses in a few different areas, different areas of applied optimization. So I've done a lot of work in scheduling, various types of scheduling problems, done a lot of work in vehicle routing kinds of problems in terms of research. I've done some of my other research is focused more broadly in general application of artificial intelligence, engineering systems that use artificial intelligence. And another area that I do research in is actually in pricing and revenue management. This is something for me, it's a little bit more recent of a research area that I've gotten into not long ago. But for me, it's something that's a very interesting research area as well. In addition to my work at Mary Washington, I'm also part of a small consulting company called Polyad Decision Sciences. Interestingly enough, it started off from some consulting work done here at the university. We wound up working with a customer, built an optimization system for them in the transportation industry, and it turned into a software services product, which really grew beyond the scope that the university could support. So, from that, an independent company rolled off an independent company, and now basically what we do is we do the same work for clients in a lot of different industries. We build typically custom decision support systems that help them with problems that they can't find out-of-the-box software, pre-existing software packages that can solve. So that kind of ties nicely together with my work at the university. They tend to be pretty interrelated in terms of the kinds of work that I do in both contexts. But that gives me a little bit of background, and I've seen optimization from a lot of different perspectives here. And so I'm excited to be able to share today a little bit about revenue management. So as we get into this topic of revenue management, Most of us have probably at some point encountered at least the effects of revenue management and been on, a part of it in some way. If you've ever bought plane tickets, you've seen revenue management at work, and you've probably noticed the impact that timing has on the price. So, for example, you might find that you book your flight 6 months in advance, and you pay $200 for a seat, a relatively inexpensive seat, and then the very seat next to you, which is, at least physically looking at it, it's perceptible, it's really indistinguishable in terms of how different it is from your seat. But the person sitting in that seat paid $3,300 for their seat, which they reserved the day before here. And so, why such a large difference for seemingly the same good? Obviously there's a difference in timing, but why is that results in such a huge price? So this is revenue management at work. And by the way, we see this, not just in the airlines, but we see this in many other industries as well. For instance, booking a hotel or reserving a rental car, scheduling a tea time at a golf course. These are all different areas where we see revenue management at work. And so, what's behind this difference in pricing? How does that work? And how do companies do this appropriately? And the answer is revenue management. This is revenue management at work. So when we talk about revenue management, a definition I would give to revenue management is the science of maximizing revenues attained with existing capacity through the use of advanced analytics. And we're going to see as we look at the overview of revenue management, it really is a lot of advanced analytics. There's a lot of different things that come together. Optimization is one piece, but it's definitely not the only piece. So when we talk about revenue management, the goal basically is this, is to sell the right product to the right customer at the right time, through the right channel, at the right price. So again, we have lots of rights. You can see there's a lot of different things that have to be coordinated and lots of things that have to be found out the right quantity and coordinated and basically worked out in tandem. So each of these rights is something that's an unknown. The right product, the right price, the right customer, the right channel, all these things are unknown and they have to be determined. So as I mentioned, we've already talked a little bit about this. There's a wide variety of industries that revenue management is being applied to, and it seems like it's growing. The list is growing, and it's really the field seems to be evolving from its traditional use. It really started in the airlines here in the U.S. in the 1980s when they basically deregulated airline pricing, and so some of these new airlines were developed that had really low fares and were beating out the old established players. And so through the use of revenue management, the old established players were able to get their footing back and actually, really find a new way to increase revenues dramatically. So we find some conditions, that characterize industries that are appropriate for revenue management. So we typically find it works best when, we have a couple of different conditions. One of these is a fixed capacity. So as an example, a rental car business might have, let's say, 20 luxury cars and 40 compact cars. And that's their capacity that they can work with. Or another example is that a plane has 50 seats that it can sell. So it's constrained in that sense. Similarly, an airline has a fixed number of different types of planes in its fleet. Also, typically we're dealing with perishable goods or services, at least traditionally. Although things are evolving, as I mentioned, revenue management, the way that they're starting to apply it to new types of industries is starting to evolve past, requiring these things. But traditionally, cases where you have perishable goods or services is important. For instance, when you're thinking about a rental car business, when a day passes, if you have an unrented car or an unrented booking slot where there's demand, but you don't allocate cars, that's forever lost revenue there. When a plane takes off and there's unsold seats, that's basically lost revenue. They can never recoup that specific revenue again. So you have this notion of perishable goods or services. And similarly, there's the reservation of resources or services ahead of time. Now, of course, this doesn't preclude last minute spontaneous sales. So in the rental car industry, walk-ups are very common. It's just part of what you plan for. A walk-up is where a customer doesn't make any kind of internet reservation. They just walk in and say, I'd like to rent a car today. Tell me what you have. Again, you can forecast that just like you can forecast other types of reservations. So, the idea though is that you have a set of resources there's typically some form of reservation of these resources or services ahead of time. So when we talk about revenue management, there's really 4 key activities that we're talking about here. Most revenue management systems consist of a combination of all four of these in some permutation, in some mix. Now, what differentiates one industry from another is the part that each of these different places, each of these different activities is going to play in making the revenue management process happen. So one of the first things we have to do is we have to segment the market. And this is more, this requires, obviously some analytical work, but a lot of creative insight, a lot of insight into the customers to realize that you have different customer segments. So for example, as we're looking at the airline industry, um, you look at two different seats, one seat next to another, one seat can generate $200 and another can generate $3,300. Looking at that, just the physical capacity, it looks identical, right? But it turns out there's different types of customers and different types of customer segments that want those seats. On the one hand, you have leisure flyers who book far in advance and they're looking for low cost. They're looking for paying low prices. On the other hand, you have business flyers who have a big deal they need to go make in another city across the country or out of the country the next day. And paying $3,300 is just a drop in the bucket. It's nothing to them. And you can see actually if the airlines only sold allowed all their seats to be taken by the leisure flyers, you notice what happens. The business flyers who really need those seats, there's no capacity left for them. So you can see, by coming up by seeing these different segments in the market and planning on making sure that you're actually doing a service, you're actually doing something that's very helpful for the business flyers. You're ensuring that they have that capacity. And the way that you're ensuring that is through the price differencing that takes place here. So again, the way you segment the market is you have to think about the capacity that you have to offer, and you have to think about what that capacity actually means to the different market segments, and how they value that. And you charge prices that are appropriate to how that capacity is valued by those different segments. So this is a key part, the idea of segmenting the market and determining the different segments that you're dealing with. Another aspect, a very critical aspect, is the pricing itself, determining the right prices. And so there's going to be a price response from each segment. When I say price response, demand and price are connected. And so generally, if you can imagine a graph, where you have, demand on one axis and price on the other, as you increase in the price dimension, the demand is going to go down. So when you have a good that's highly valued, when the price is very low, the demand is going to be high. And as you increase that price, the demand is going to go down. And so, one of the goals is to adjust your prices to match capacity. And so in some forms of revenue management, this is really the determining the kind of the key piece, where you don't have, the main thing is, you have a fixed capacity, and you're adjusting, it's easy to allocate to, and you're adjusting the price to have the demand just meet what you're able to serve with that capacity at the highest price. So as you adjust it higher than what happened than that point, then you're going to have some excess capacity that's not being used because you make the demand too low. If you put it too low, you're going to be using all of your capacity, but not getting the highest price. And so some industries, kind of moving that lever, this is the essence. This is the kind of the key driver of the revenue management. So I'm thinking, for instance, here in the U.S., a lot of real estate investors buy short-term rental properties. They're very lucrative. So if you have a unique place, there's not a lot of competition, maybe a nice place up on a unique mountain, and the idea is just to move that price up so that you just keep demand constant throughout the summer, and then maybe in the winter time, where there's a lot less demand, you lower the price to actually stimulate demand. People say, "Oh, I can get a good deal," and I lower the price there. So the pricing, impacts the demand substantially in certain industries. Now another aspect to pricing though is competition. And so when you have a highly competitive scenario where there's lots of competitors, prices don't work like that. You have to take into account also not just the price response from your customers, but also what's being offered by your competitors. So the rental car industry is much more characterized by competition. In virtually every city, you find all the big players there, and they are, offering their products. They're all competing against each other, and so prices are constraining each other by that. So that makes a very different kind of competitive environment. Another aspect here that we have to do is we have to forecast demand. The idea here is for each demand segment, typically in revenue management, we're working over a defined time horizon. In the rental car industry, in real life, time horizons of about 45 to 60 days are pretty common. The idea is to forecast the demand for each different segment for our individual booking slots that are possible. And then, this gives us something to work with to be able to plan how we're going to meet that demand in a way that maximizes the revenue. Now, again, this is something also that's constantly changing. Just like the prices are going to be changing. Taylor Swift comes into town. We find out she's going to make a surprise appearance in 2 days. All of a sudden, the demand is going to be really high for, rental cars. Similarly for demand, demand changes. The forecast is not a static thing by any means. And typically, when we're looking at forecasts, the near-term forecast tends to be more accurate than forecasts farther in the future. And it would behoove us, we want to be wise about this. We want to understand that, forecasts are changing, and we want to make sure that we're able to constantly integrate the changing forecasts and the demand variability into our decision making. So all these are, some of the key pieces. And now this last piece that we have, which is really going to be the focus of our work today, is optimizing capacity allocation. So when we have the demand, these different demands from different segments at different price points with our capacity over a horizon, we need to figure out, how do I take this capacity, and how do I allocate that to the demand in a way that's going to maximize our revenue? And this is really, the way that we, kind of turn this knowledge that we have from the market segmenting and the right pricing and the demand forecast into actually reaping the high revenues, and really taking out as much from the market as we're able to, and generate as much value from the market as we're able to, which is through this capacity allocation. And this capacity allocation really is optimization. We build, in practice, linear and integer programming models, which is what we're going to be working with today, are typically the way that it's done. So as we move, I'm going to pause here and just ask, are there any questions about the big picture of revenue management before we continue? Okay. So I want to take us into our first scenario here. And again, as we're talking about the rental car industry. So one of the things that characterizes the rental car industry, again, each industry has unique characteristics that, require tailoring the revenue management approach to. So with the rental car industry, there's a couple of things. One of those is, it's characterized by high competition. As I mentioned, every city is going to have a lot of different competitors, and uh, that of course impacts the pricing. We can't just use price as a pure lever, to control demand, because our competitors constrain that. So pricing is a smaller part. It's obviously, it's constantly changing due to, the changing market conditions, the changing demands, but it doesn't have the same control as it would in other industries, in our ability to stimulate demand, or to control the demand. So it's, we treat demand as a little bit more fixed, I should say, more constrained in this industry. Another thing that we have is, unlike industries like airlines, or particularly like in hotels, for example, is a good contrast. In a hotel, you have a very fixed capacity. You have a fixed number of rooms, and that's never going to change at a particular location. In the rental car industry, our fleet is a little bit more flexible. So our capacity actually has a bit more flexibility than we find in other industries. For instance, if you're going to have a big demand, if you're across multiple locations and you're going to have a big surge of demand in a particular location, well, what you can do is you can move some cars, you can pre-position some cars from other locations to be there, to be ready for that demand, to meet that, and generate extra revenue. So we have a kind of flexibility with our capacity that we don't see as much in other industries here. So as we talk about the rental car industries in the scenario here, what we're going to do, we're going to start off with a single location. And as I mentioned, we're going to build into more complex scenarios here. So in this first scenario, and again, the first three scenarios, we're going to assume fixed conditions. And then in the last scenario, we're going to see how we extend what we have to incorporate changing forecasts and to incorporate dynamic pricing. So in this scenario, we have a single location rental car business. So just one location, not multiple cities. And let's say we have three different car classes. We're going to have a compact cars, and we'll say we have an inventory of 35, midsize with an inventory of 80, and then luxury with an inventory of 50. Okay, and we're going to use rental durations ranging from 1 to 3 days in our scenario here. In reality, there's a lot more. You can have 1 to 4, up to a week is pretty common. Sometimes people will rent a car for a whole week. Past that, that's also possible. But in either case, if we just have, 1 to 3 day long durations, that kind of gets the essence, is that we have a fixed set of durations here. And so another thing to think about with the rental car industry, and we also see this in other industries, is this notion of substitutions or upgrades. And this might sound like a bad idea. It might sound like you're wasting your higher quality goods, your higher class capacity. But this actually, by allowing for upgrades and substitutions of one product for another, this allows you to make even more flexible use of your capacity. And we'll see this tends to generate more revenue if you allow this here. So for example, let's say I reserve I go to book a car at a location, and then I go to pick up my car on that day. Let's say I rented a Prius, and they come to me and they say, well, I'm sorry, we're out of Priuses. We're going to have to upgrade you. You're going to get a Ferrari today. So you can see, not a lot of people would be upset at exchanging a Prius for a Ferrari. Or when you go to rent a room, you get a one bedroom hotel room, and you get upgraded to a two bedroom or something like that, a nicer room. So you can do that, and this actually is a win-win because the people who are getting the upgrade get the unexpected surprise of a good experience, better than they had anticipated, and the companies can make more flexible use of their capacity. So through each of the scenarios, we're going to see the impact that substitutions make. You can allow substitutions, or you can just say no substitutions. If they're asking for a compact car, they have to be allocated a compact car. And then again, each scenario will have 7 days of forecasting data here. So again, what we see, this is a sample of what we'll see in the real data set for this first scenario. You can see here each row is a specific booking slot. So for instance, this first row is a booking slot for a compact car, which is going to go out on day 1, and it's going to be returned on day 2. We can see we have 16 of these, and the price for this is going to be 50. And the next row is renting out on day 1 for a compact car, but coming back for day 3. So that's a 2-day slot, and then this third one is a 3-day slot. And we can see the demand and the price forecasted values here. And then we move to the midsize. Here's a midsize going out on day 1, coming back on day 2, and so on and so forth. Okay, so we have a lot of these. You can see there's a lot of different demand slots that are possible. You can see there's overlapping demand slots here. So for example, if I allocate a car to this first demand slot, I can't allocate it to this one or this one, because there's an overlap there. So we have to think about this. Again, this is where optimization comes into play, is to think about how to allocate our capacity intelligently so that we can maximize the revenues. So I want to move on to how we frame the problem. And again, I'm going to frame this in terms of what we know and the decisions that we have to make. And then, we're going to look at how we actually model this mathematically. So again, with node entities, these are going to be the things that we have given to us, the things that we're going to know before we go and make any decisions about, about how to allocate our capacity. And so it typically breaks up into sets and then parameters here. So with the sets here, we have the set C, which is going to be the set of car classes. So this is going to be luxury, midsize, and compact. And S is going to be my set of booking slots. Okay, and then we have some parameters. We're going to let delta be my number of days in the planning horizon. You'll see why I'm using delta rather than D in just a second. Okay, and then we have PK, which is going to be the price per instance of car rented for slot K. Okay, so again, going back to this here, this is my PK. This would be, for instance, P1 and P2 if we number our demand slots here like this. DK is going to be my demand for slot K. Okay, so you can see how I'm using the index K. The index K is going to, in our modeling, is going to go over the set of booking slots here. Okay, then I'm going to have a set DJ. Again, this is a set, but it's a parameter since it's based on a booking slot or based on a departure, a particular day. DJ is going to be the set of booking slots that have cars departing on day J. So for instance, let's talk about day 1. If we go back here, you can see all these demand slots, demand slot 1, 2, 3, if we just number the demand slot 1, 2, 3, 4, 5, 6, all these depart on or are rented out on day 1, right? So all these would go in capital DJ. Okay, and AJ, this is the set of booking slots with cars arriving on day J. Okay, so these are the cars that are being returned. So if we go back here and look at this, for example, looking at day 2, you can see day 2, slot 1 is returned on day 2, and then slot 4 is also returned on day 2. And if we go down farther, we'll see others. So these would all be part of the AJ, capital AJ. And you can see J here, the J index is going over, starting from the first day and going up to and including the last day in the horizon. Okay, and then we have inventory. So as we think about inventory, the way we're going to handle making sure that we don't allocate cars from one slot, they're incompatible with another slot, the way we don't do that is we're going to track the inventory flows here. So we're going to make a parameter here, I, which we're also going to have a corresponding decision variable, but this is going to be one just for the initial. IH0 is going to be the initial inventory of car class H. So for example, if we look at H, if H is compact, that's going to be I, compact is going to be 35. I midsize 0 is going to be 85, and I luxury is on day 0 or at the beginning is going to be 50 here. So these are our initial inventories. Okay, and then when we talk about substitution, we're going to use this variable VHK, which is going to be either 0 or 1, sorry, parameter VHK, which is going to be either 0 or 1. It's going to be 1 if car class H can be used to satisfy demand slot K and 0 otherwise. So for example, if we're not allowing substitutions, V compact slot 1 is going to be 1, and everything else, V midsize slot 1 is going to be 0, and V luxury slot 1 is going to be 0. If we're allowing substitutions, where a higher quality car, a higher grade class can be substituted for a lower, then V compact 1 is going to be 1, V midsize 1 is also going to be 1, and V luxury 1 is going to be also going to be 1. So this just we can use this to control our to control our substitution policy and to swap out substitution policies. Okay, so these are going to be the known entities here. These are known ahead of time, and when we go to make our decisions, again, our main decision we have to make is for each booking slot, how many cars of each class have to go to that booking slot. So we're going to let XHK be the number of cars in class H that are going to be used to fill slot K. Okay, and then IHJ, again, it might not be obvious why we need an inventory variable yet, but again, if we're going to track inventory from one day to another at the location, cars coming in, from, being returned and cars going out, being rented out, we're going to have to track this through a flow modeling. And so we're going to have a decision variable called IHJ, which is the inventory of car class H at the end of business day J. Okay, so these are the known entities of the decision variables. Now, when we go to do the modeling for this here, again, when we're going to be using integer programming, a simple form of integer programming, integer linear programming, I should say. So when we're dealing with linear programming, a linear programming model has two components. It has an objective function, which is some quantity, a linear quantity, a quantity that a linear expression that we're going to either minimize or maximize, and then a set of constraints, which are just linear inequalities. A left-hand side, which is a linear expression, less than, greater than, or equal to a right-hand side, basically, which is also a linear expression. And we have these, and this is how we model problems when we're doing linear programming here. So the objective that we're trying to do here is we want to maximize total revenue. Okay, so our total revenue is, what we're going to do is we're going to sum over all car classes and slots, the slot rental price times the cars assigned. So again, when we do the modeling, we want to think about it's easiest if we just phrase it in plain English and natural language first, and then we write it out mathematically. Okay, so if my rental price, my slot rental price, which is PK, times the number of cars assigned, is going to be XHK for some given car class H. If we want to sum that over all cars and all slots here, what we're going to do is we're going to say maximize. And then when you see the sum, by the way, if you're not used to seeing this math, this is just, you just want to think about these sums like for loops. This is just a summation symbol. It's really just a for loop, an outer for and then an inner for. So for each car class H and the set of car classes C, and then for each demand slot K in the set of slots S, add up PK times XHK. And you add those up, and that's going to be the objective function that we have here. Okay, so this is what we're going to try to maximize. Now we have these constraints that we have to respect. Okay, so our first constraint, I'm labeling each component individually, so the objective is going to be 1, so the first constraint is going to be 2. So our first constraint is for each slot, we want to make sure we don't allocate more cars than demand. And again, we do this because if you have demand, if you're allocating more cars, there's not demand for that. You can't reap any profit from cars because nobody's going to buy those cars. So for each slot, we want to make sure that we don't allocate more cars than demand. So the idea is this, the total cars allocated to a slot is simply going to be the sum from all classes that are allocated to it. Okay, so again, let's kind of work it. When you see this notation, again, if you're not used to seeing mathematical notation, this is just for loops in Python. So we'll start with this for each slot. Okay, so we have to repeat this constraint for each slot. So you see this on the right-hand side. This little upside down A just means for all. So we're saying for all K, all slots K in the set of slots. Okay, and then we're going to have this constraint that we ensure we don't allocate more cars to that slot than demand. Okay, so something that has to be less than or equal to DK, which is the demand slot for that, the demand for that particular slot K. Okay, and the total cars that are allocated to that, well, we just have to determine that. For demand slot K, we just have to sum over all car classes H in the set of car classes. So summing over all car classes H, XHK has to be less than or equal to the demand here. And this allows us to just make sure that we don't allocate more cars than demand. Okay. Another thing that we have to do is we have to ensure that for each slot, only allowable car classes are allocated, right? If we say we don't allow substitutions, we need to make sure that a compact car doesn't, or a luxury car doesn't go to a compact. And in any case, even if we do allow substitutions, we need to make sure that a compact car is not assigned to a luxury booking slot. Okay, so the way we do this here is we're going to ensure that for each slot, we're going to ensure that the allocation of invalid car classes H to that slot K is going to be 0. So in other words, XHK is going to be 0 in these cases. And to do that, we're going to use a trick that's very common in operations research, which is to use the big M, where we just let M be a very large constant. Okay, and we're going to write the constraint like this: for all car classes H in the set of classes and all slots K, XHK, the cars of class H assigned to slot K, is going to be less than or equal to M times VHK. Now remember, VHK is going to be 0 if the substitution is not allowed, or if the allocation is not allowed of car class H to K, or otherwise it's going to be 1 if it is allowed, right? So if this is 0, even if M is really large, you can see it's going to force my XHK to be 0. And if M is large, then XHK can basically be allocated as needed to this particular class here, is the idea. Now, of course, we've already seen that XHK is constrained by another, by this previous constraint here, by the total demand. Okay, so we can see here that, we don't need to think too much about what that M is. It's already set for us. Or I should say the maximum is already set by this previous constraint here. At the same time, though, I'll mention, logically, a large value of M is fine, but for solver efficiency, we typically want to try to have as small a value of M as possible. This makes the solver find solutions fast. So in this case, we can obtain a pretty tight M by letting M just be the maximum of the demand in that demand column here. Okay, and now we come to really, I think, the key constraint that ties all this together, which is the inventory flow modeling here. So we have lots of incompatible slots where a car can't be assigned to both. And so to account for this, there's a couple of ways we can do this, but a way that really generalizes to the multiple locations is to model this as car inventory flow modeling. So the idea is this: for each car class H on day J, we want to make sure that, we want to model the flow of balance of inventory, right? So the ending inventory at the end of the day on day J, the ending inventory day J, which is going to be IHJ for a car class, is just the previous day's ending inventory, whatever I had at the end of yesterday, minus the cars rented out today, plus the cars that are going to be returned today. Okay, and this is going to give us our inventory flow balance. We just repeat this across all the days in the horizon to make sure that all the cars are properly accounted for. So we're going to write this as follows mathematically, or just translating what we have in this first bullet point to the mathematical formulation. We're going to have IHJ, which is inventory of car class H at the end of day J, is going to be IHJ minus 1, so the ending inventory of the previous day, minus the cars rented out on day J, the total cars rented out on day J. So what is that? That's going to be, again, for car class H, the total cars rented out of car class H on day J is, I'm going to sum across all my slots in DJ. Remember, DJ is that set of slots that have cars departing on day J. So summing across all those slots, XHK, all those slots K, XHK is going to be all the cars that are going out that day. Okay, and then similarly, all the cars that are going to be arriving or returned, I'm going to sum across, use my set AJ. Remember, set AJ is going to be all the slots that have cars coming back today. Okay, so I'm going to summing over K, and that set AJ, XHK. That's going to be my grand total of cars that are being returned here. And then I'm just repeating this here for all car classes H and C and all days in the planning horizon 1 to delta here. Okay, and then last of all, we have to have a constraint where we just, this is for formal linear programming, we make sure that we specify the domains for our variables. So we're just going to specify that that IHJ and XHK are all going to be greater than or equal to 0 and integer, just specifying the domains here. Okay, I want to pause. I've done a lot of talking through this modeling. I want to pause and ask if anybody has any questions before we move on. Okay. So what I want us to do, we're not going to have a work through where we actually code in this first scenario. We're going to use this first scenario just to kind of see how these concepts are implemented here. So let's go ahead and I'm going to move to the notebooks, and you guys can feel free to do the same. So we have two notebooks. We have the learner and we have the I'm just gonna go ahead and do a run all for this so we can kind of go through this and kind of see it together here. So the learner notebooks, as you guys know, have some to-dos for you to work through to implement some of this modeling into the code here in Python. And so we're gonna as we work through this, so this first scenario, I'm just gonna explain the framework that we're gonna use, which is called Pulp here. So we'll go ahead and look at a couple of scenarios here. So the first thing I'm gonna do is have a couple of some code here that's gonna help us. We don't really have to do a whole lot with this. This is just going to be used for, auxiliary for some of the things that are to come. But if we look at the first scenario here, when we read in the data set, this is what we see here. Again, this looks just like what we saw in the slides here. This is how we specify our initial car inventory. I'm going to be using dictionaries. And then I have two different types of substitution schemes. One where I have no substitutions, and then one where I have upgrades. So for instance, compact can be upgraded to a midsize, and compact can be upgraded to a luxury, and midsize can be upgraded to a luxury here. So this is the data that we're going to be working with in the initial scenario. And as we look at this here, one of the things that's always a good idea to do is to look at the demand pattern. So I'm going to just do this briefly here so we can kind of see, the luxury tends to have over these 7 days the lowest demand. The midsize and the compact tend to have somewhat higher demand for this. And you can see the demand fluctuates from one day to another. Okay, so when we do this, the framework that I'm using in all of the modeling is a Python framework called Pulp. And what it does is it allows you to create very nice, terse algebraic modeling. One of the things I really like about Pulp is that it's very close to the mathematical formulation. It doesn't require lots of object-oriented notations and these kinds of things. It just, if you can do your model on paper, it's very easy to take that and put it into the format that's needed by Pulp here. So I have, for each of the models, you're going to see that I have two different components. I have beforehand a component here that's going to allow just the raw data from, what we just read into pandas and, that we created, in the dictionaries, these things here. It's going to take this kind of raw data that we take and it's going to format it into what's needed, into those inputs that we saw in the modeling here. It's going to align it exactly here. So in each case, there's going to be a function that builds the model inputs here. So this one builds the single location model inputs from the demand data, the inventory, the initial inventory, and the substitution schemes here. Okay, and now we come to Pulp, and this is where I'm going to, what I'm going to do is in each case, we're going to have a function that builds our model. It's going to build a Pulp instance, a Pulp problem instance, which can then be solved. So the nice thing about Pulp, if you're not familiar with it, again, it implements mathematical programming, so you can do linear and integer programming very seamlessly, and it also makes it very easy to swap out different kinds of solvers here. So there's some very nice open source solvers. It works obviously with with things like Gurobi and Cplex. Those are ones I use in consulting and in research here. But in terms of getting a model going, it comes pre-packaged with the CBC solver, which is a very nice solver to get you started. And then Highs, works very seamlessly with Highs too. If you're not familiar with Highs, it's a great solver. It's an open source solver that has performance really that approaches the proprietary solvers. So Pulp allows you to switch those backends very easily here. So what we're going to do here is let me get this just a little bit up here. As we do this, you'll see here that the params here, all the inputs to the model, to the build single looking model, these are the same exact ones that we saw in the paper modeling, and that's intentional. That's just to mirror this so that when we implement, it's relatively straightforward. Okay, so as we do this, I'm going to compute the big N. So one of the things that we're going to do is we're going to specify our decision variables here. So our inputs that we have all come through here. Okay, so what we're going to do is, you know that we're working with indexed variables, and if you're used to using other frameworks, you typically think of these as arrays. In Python, a dictionary is a very flexible way to do this. You can use indices that are not just numbers, but words, compact, medium, and luxury, compact, midsize, and luxury, for instance, can be used here. So we're going to make our variables, using lp variable.dicts. This is going to create a dictionary of variables, in this case called X. Okay, and then you can see it's going to be indexed over car classes C and booking slots S. Okay, and it's going to have a minimum of 0, a minimum value of 0, and a maximum no maximum value. And we're specifying that this has to be an integer. Okay, and then our variable I is also going to be uh, a dictionary as well. Okay, and we're going to do something. I know that we said I H0 in the past was a constant, a parameter, and then uh, IHJ basically was going to be the decision variable. So in this case, we're going to make the IH0 a decision variable. That information comes in through D through yeah, the I comes in through my I0. So this is what I'm going to do is just have a constraint that sets those here. So we create our two variables like this. Okay, and then we're going to create a pulp model here. So we're going to say we're going to do this a variable called mod, which is going to be an LP problem. We're going to call it single loc RC is the name, and we're going to specify the objective, which is to maximize. And now the way we add components to the model, the way we add a objective function or the way we add individual constraints is just the plus equals, just like we're used to doing when we add something to, onto it, we append to arrays. We're just appending another component onto the model. So we're going to, as we add the objective function that we're going to have, we're going to say mod plus equals. Again, this is just our objective function that we saw before. We're going to sum over each car class H over each demand slot K, PK, which is the price of that slot times XHK. Okay, and we're going to call this total revenue. Okay, so this adds our objective function. Okay, and now what we can do is we can proceed through our constraints, just like we saw before. So we're going to add constraint 2 to this. The first one here is to ensure that we don't allocate more cars to a slot than there is demand. So we come back to this. Okay, we can see what we're doing is we're going to say for K and S, so we have to repeat this constraint. If we look, it's repeated for each slot K and S. We're going to say mod plus or equal, or I'm sorry, plus equals sum for H, for each H and C, XHK has to be less than or equal to DK here. So notice how close this is to the algebraic modeling that we did on paper. You can see here, this looks just like it's pretty much verbatim the same thing that we have just in code. And this is one of the nice things about pulp. It allows that very, very verbose or very terse modeling here. Okay, and then we'll go here and we'll, add our next constraint, which is to ensure, again, this double for loop here to ensure that we don't have any invalid substitutions. Okay, we're going to set our initial inventories. Remember, I is a decision variable, even for index 0. So what I'm going to do to set my day 0 inventories, we can think about day 0 as the preconditions before the actual time horizon starts. I'm going to set those for each car class H. I'm going to set IH0 is going to be the inventory 0 that this comes in as a parameter H. Okay, and then last we're going to implement our inventory flow balance. So for each day J in range 1 up to delta plus 1, again, this is the way Python does it. When it does a range, it starts on this value and it goes up to 1, basically whatever ends in this range minus 1. So this is just covering the entire range of days in the planning horizon. Inventory of car class H on day J is going to be equal to inventory car class H on day J minus 1 minus the sum of all all slots in the departure for today for day J, they're allocated, plus the sum of all cars in class H that are in slots that arrive on day J. Okay, so we just have our inventory flow balance here. Okay, and what we're going to do now is we're going to, just as a scenario, I'm going to show what we can do is we're going to build our models here. We're going to make two different instances of the model. We're going to make one where we solve with no substitutions and one where we solve with substitutions. Okay, and when we solve that, we can see a difference here, right? We can see, the profit that I make when I allow upgrades is I make 86,951. Whereas if I don't allow the upgrades, notice my capacity is not as flexible. I'm only able to reap $82,023 from the market here. So this here, by allowing the upgrade over the 7-day period, this generates an additional, almost an additional $5,000 here, like this. So you can see the benefit that happens when you allow upgrades. One of the things I want to show, so again, what happens is, when we solve a model like this, we're going to get a plan. This is going to tell us here. Now we see the demand and the price. So basically we're adding some columns. We're saying, now for this slot, how many compact cars do we allocate to this slot? Well, we're going to allocate 11 compact cars and 5 mid-size cars. And in this slot here, we're going to allocate 17 compact cars and 3 luxury cars. So this is going to show us what the actual allocation plan is that we can actually go, somebody could take this and go and execute this plan. Now keep in mind, things change. This is a static point in time. This is not going to be fixed. We have to modify this as time goes on. But this gives us a working plan to work with. Okay, one of the things I want to do also, just to showcase, we're not going to do this for every scenario, but what is the value that you get from revenue management? If we contrast this with the way a human might actually make these decisions, the one way might be somebody stands in front of a phone or maybe a computer is connected to a server. There's a server there that takes these requests, but the requests basically are given no substitution and in first come, first serve order, right? And so if maybe a particular car class comes in, a booking comes in for a car class that's not particularly profitable, that might take away cars from another, notice that's just going to be what's served first, right? So there's a lot of variability in what can happen here. So I've got a short, a function here which is going to simulate that first come, first served decision making that might happen the way a human would do this without revenue management, or maybe a simple computer algorithm that just takes the reservations as they come in. And this is just going to allow us to see different policies here. So what I'm doing here in this as a simulation is we're going to run this 20 times at random, randomizing the order of the requests that come in for all the demands. And we're going to see the results here. So if we look at this and visualize, we look at the two policies of, the revenue management with upgrades and the revenue management without upgrades. We can see here that, the first come, first serve, it ranges from about 51 to about 55, 54, $55,000 here. But then when we look at the values here, for the revenue management, then it jumps up. The no upgrades gets us to 82,000, and the upgrades gets us to 86,000, almost 87,000 here. So you can see the impact. You can see just why companies want to use revenue management. It really does deliver value, delivers real value, and especially in cases like this where a precise allocation of capacity to demand, a strategic allocation in an intelligent way, can really, really reap financial rewards here. Okay, so I'm going to pause here. I've kind of gone through this. Really, my goal with this first scenario was to show the modeling and to kind of show how we implement this in Pulp before I have you guys work a practice problem here. I want to pause. Are there any questions on what we've talked about? I've been doing a lot of talking so far. Manuel?
Yeah, I have a question. I was posting in the chat, but I mean, for me, so I'm going to read my question actually. I found interesting that our decision variable is how many cards do we assign to each slot
Mm-hmm.
instead of which price do we assign to each card type in each point on time. So, so my first question is, what is the difference between these two modeling approach? Does that make sense? I mean, my
That
intuition would
makes
be to
perfect sense.
model first. Okay.
And you're asking a key question. And by the way, I'm kind of I'm assuming some magic is happening here to give us these demands and these prices here, right? But what's actually happening in reality is there's a pricing engine which is monitoring conditions. It's also working in tandem with a forecasting engine.
Okay.
We're looking at forecasting and we're looking at pricing. And the pricing, by the way, happens through a couple of things. The pricing typically is determined first, it's determined through pricing experiments to see the different demand segments. How do they react to price changes? And so through slow and gradual pricing changes, you can kind of test the waters and see, okay, this is where demand starts to fall off on the one hand. But the other thing that's factored into that is the competition, right? What's going on? How are competitors pricing? Because again, if you're priced high, even if the demand would normally absorb that, if your competitors are priced lower than that, they're going to go there before they go to you. So the pricing engine is constantly working, and similarly, the demand forecasting engine is also constantly working, and these two are working in tandem to give us those prices and those demands that we're working against here. So in a sense, it looks like magic. It kind of is. We're isolating this one part of the problem and just focusing on the capacity allocation right now. But as we talked about before, all that is happening as well. Those are other components of revenue management. I wish we had more time to talk about those and actually kind of showcase how some of those work. But in this discussion, we're going to be focusing mainly on the capacity allocation.
Yeah, no, makes sense. But so if I get right, so what you're saying is that the thing is that we are not considering competitors, and the price could change, but the allocation should not change if the price are properly matched to competitors or to the environment. Something like this, right?
Sort of. Well, the pricing and the pricing and the demand forecasting is going to be constantly
Yeah,
changing.
yeah.
Now, of
Okay.
course, in the near term, it doesn't change much. As you look farther in the future, the demand forecasting gets less accurate. But the pricing is, changing on all kinds of factors. For instance, a major politician might be coming into town as a surprise. All of a sudden, the next day, demand was one thing, it shoots, and so does then the prices do. Competitors all raise their prices together. But all that has to be monitored almost in real time. Those are all things that are happening on
Mm.
the pricing engine and the demand forecasting engine. And those are constantly giving us these values. We're looking at it as a static snapshot. We're formulating a plan which is going to, it's meant to be broken. It's meant to be changed, and what we're going to have to do as we work through the scenarios, we're going to see how we can formulate this in a way that it can actually adapt to those changes. When changes happen, we can reformulate based on what we already have committed. But then, we're also going to be able to absorb these constant changes that are happening here. So in reality, one way that this is often done is by using those pricing and demand forecasting, and we're constantly updating our capacity allocation.
Got
We're
it.
constantly adjusting our plan to meet that. So the plans are, it's a plan, but of course it's never static. It's always changing as conditions are changing.
Got it. Thank you.
Other questions? Okay, let's go ahead and take a look at our next scenario.
Before you continue, I'm sorry, I can't find the raise hand button here.
Oh,
This capacity allocation, I mean, you can't make an economy car luxury car. So I'm assuming you're allocating a certain number of economy cars to different price segments. Is that right?
that's exactly right. We're accounting where they can be actually where they're allowed to be allocated. So an economy car, a compact car, obviously, as you mentioned, it cannot go to a luxury car. The reverse can happen if your policy allows for the substitutions. But that's exactly right. Each demand slot, each booking slot is going to have a demand for a particular type of car class. And, again, if you have a lower class, let's say there's a demand slot that has a compact car, and so let's say they demand 15 compact cars for one day. If you allocate, a compact car, you can meet that. If you allocate a luxury car, you can meet that as well. And so the idea is what we have to figure out is for these demand slots, how do we allocate cars appropriately across these different booking slots? And there are multiple slots that demand a compact car. There are multiple slots that demand a mid-sized car, and there are multiple slots that demand a luxury car. And so given the capacity constraints that we have and whatever substitutions are allowed, how do we do that optimally?
So I might have one and the same car at multiple different prices.
For different segments, yes. And so again, think about the analogy with the airline.
Yep. Yep.
One
No,
a leisure
I
flyer
get it.
buys. Go ahead.
Yes. Yeah. I hear you. I get that. What I'm wondering is, I mean, so what is the decision that we can't reverse tomorrow? Is the cars we gave out today, is that right? Or
Yes.
reservations we accepted?
hmm Reservations to include walk-ups, which is where they just come up. They didn't make a reservation in advance. They just come in and say, "Hey, do you have a car available for me today?"
Now, what I'm trying to understand is what do we use the output of this optimization model for?
To plan. This makes sure, for instance, that we don't promise more cars to one slot than is going to be profitable for us.
Right. So we limit the number of cars that will be sold in a particular slot.
Exactly. And what this does, this optimization model ensures that we can actually allocate the cars that we do have to those most profitable slots, in a way that maximizes the total revenue.
Gotcha. Okay. And I mean, would it make sense to do this under uncertainty rather than deterministically?
Absolutely would. Yes. This is a simplification. These first three scenarios are a simplification. Really, all this, is, it gets into some realistic aspects here, but, all this is very just scratching the surface in terms of revenue management. It's really intended to build a foundation, but the first three scenarios, again, for the modeling piece to kind of showcase the concepts behind it are going to be assumed static. And then in the last scenario, we're going to see how we incorporate the changing prices, because in reality, prices are constantly changing, and so are the demand forecasts. Demand forecasts are always fluctuating, especially as we look farther in the future.
Right. Thank you.
Yeah. So let's take a second. I'm going to move to the next scenario here. So I want to look at a new scenario here where we add a little bit of complexity. And what we're going to do in this case is we're going to assume that we have multiple locations here. Again, we're going to make some simplifying assumptions in this case. This isn't, typically how cars would be transferred, but this gets into how I mentioned earlier that in the rental car industry, we have some flexibility with our capacity. How does that actually work? We're going to see how we use our capacity a little bit more flexibly when we look at this scenario here. So we're going to have a multi-location rental car business. We're going to say instead of just one single location, we're going to have locations in 3 different cities here in Virginia, which is on the east coast of the U.S., Fredericksburg, Charlottesville, and Arlington. Again, we're going to have our same 3 classes, a compact, midsize, and luxury. But one of the things that we can do is we have the ability to transfer cars from one location to another. And again, this is one of the things that rental car companies can use to increase revenue, to make their revenue management more efficient, is to pre-position some inventory in cases where there's going to be a demand spike. It allows you to capture more of that. When you have demand spikes in the rental car industry, both demand goes up and price is going to go up, as is the case in other industries as well. So what we're going to do, though, is we're going to make an assumption that is not very realistic. It's not economically scalable. But we're going to assume that there's a fixed cost per transfer. It depends on maybe the distance from one location to another. In the scenario, we're actually just going to assume that all the transfer costs per car are the same. But this is a per car transfer. We're going to see here that doesn't really map to reality. You would have to, in big cases, you would have to have an army of car drivers to go back and forth, maybe. So this doesn't scale well, but this is going to illustrate, this allows us to transition to something that does reflect reality more here. And again, the question we're going to ask now is, how do we position our inventory and allocate our fleet to the booking slots? Okay, so just to kind of showcase what we have here, this is Virginia, and we have our 3 locations, Charlottesville, Fredericksburg, and Arlington. And so, with the demand spike, we're going to have to move cars around from different locations here in order to maximize the revenue that we can have. We want to do this, use our capacity as effectively as possible. Okay, so as we get into framing, again, what you're going to see is we move from one scenario to another in terms of the modeling here and the framing. I'm going to keep the stuff that we had before completely unchanged in black. Things that are from the previous scenario but have been modified in some capacity, I'm going to put those in blue, and then something that's brand new, I'm going to put that in green here. So the new piece that we have here in terms of the known entities is first of all, we're going to have a set L. We're going to have a set of different locations here. So L is going to be my set of rental car station locations here. Okay, and then we're going to be adding a cost here. We're going to have CHI prime here. And this is going to be the transfer cost per car of class H from location I to location I prime here. So I and I prime are both elements in this set L here. They're both locations here. Okay, and we're going to modify a couple of our parameters here. Instead of just DJ, which is a set of booking slots with cars departing from on day J, we have to have this for each location. So instead of just DJ like we had before, we're going to call this DIJ. So DIJ is a set of booking slots with cars departing from location I on day J. And AIJ is going to be the set of booking slots with cars arriving at location I on day J. So this is my departures and arrivals. Similarly, we don't have just one location, so we have to adjust our inventory for each car class to reflect for each day, also the different locations. So instead of IH0, we're going to have IHI0. Okay, and this is going to be the initial inventory of car class H at location I. Okay, now we're going to use our same variables because again, the booking slots are going to be, we don't have to think about the actual location of the booking slots because that's reflected here in the DIJ and the AIJ. Okay, but we're going to adjust our inventory variable to be IHIJ, which is the inventory of car class H at location I at the end of business day J. Okay, and then we're going to introduce another variable. So the way we're going to model this is we have our different locations, cars go and come during the day, and then at night, after the one day, but before the start of the next day at night, the cars are going to be transferred over. So we're going to let THI prime J be a decision variable that's going to tell us the number of cars of class H transferred from location to I to location I prime on night J here. Okay, and these are going to be the decision variables that we're going to use. Okay, so we have to revise our objective function a little bit here. So the same revenue is going to be there. The same initial piece here that we have is going to be reflected here. This is going to be the revenue that's generated. But we also have to subtract out of this the total cost And now the costs that we're incurring in this model is going to be the transfer costs, of cars for each, transferred for each location to each location each night. So again, this gives us a long sum, a quadruple sum. But again, remember, this is just a series of for loops adding things up. So I'm going over all car classes H, and all locations I to all locations I prime over all days starting at day 0 and going up to, but not ending on the very last day on the horizon. The cost of the transfer of car class H from location I to I prime times the number of cars transferred of class H from I to I prime on night J. So we're just going to subtract this component from the objective function here. Okay, and then the next big change that we have to incorporate here is we have to revise our inventory flow modeling here. So we're going to have a modified constraint 4. Okay, so for a given car class H at location I on day J, again, so I'm going to start off like this. Again, so this is the 4 part in the model here. For all car classes H, all locations I and L, and all days in the horizon 1 up to delta. Okay, we're going to repeat this constraint. The ending inventory is going to be the previous day's ending inventory minus the total cars transferred out in the previous night, plus the total cars transferred in the previous night, minus the cars rented out today, plus the cars returned today. And that's going to give me my final ending inventory on day J here. Okay, another thing that we have to make sure of, again, so all we did was take that last constraint and just modify it. We added in the transfers into the flow balance. We have to add another constraint here to make sure that for each car class H at each location I on each night, we need to make sure that I don't transfer out more cars than I actually have. Okay, so what I'm going to do is, again, for all car classes H, all locations I, and all days, or I'm sorry, all nights from 0 up to this, the very last night, I want to make sure that my total cars transferred out for that car class from each location I to each location I prime, for this location I, doesn't exceed my total inventory, my ending inventory that day here. So this makes sure that I don't send more cars out from a location than I actually have here, is what this does. Okay, and then, last of all, for our technicality, what we need to do is we need to revise the variable domain constraints 6 and 7 here. So Hij is going to be greater than or equal to 0 and integer. Again, we're going to do this for all car classes H, all locations I, and all days 1 to delta. And then I'm going to add something similar here for my transfer, my decision variable for my transfers. Just going to include this here to make sure that this is greater than 0 and also integer. Okay, let me pause here before we actually move on. Any questions, guys, on the modeling so far? Okay, what I'm going to do briefly is I want us to take a look at the components here. I'm going to go back to the notebook, and we can take a look at scenario 2. Okay, so again, what I'm doing here, this is a piece here to you don't need to modify this. This will read in from the raw inputs the data and produce a set of inputs that the model itself actually needs. Okay, in a second here, what I'm going to have you guys do is work through implementing some of these constraints just so you get a feel for what it's like to work with pulp here. So what you're going to want to do is use the previous model, look at how we added components to the model, and we're going to take a couple minutes and work through this. Okay, but before we do that, I did this a little bit later. Just want you guys to have a look here. Again, this is going to show us what the data looks like here. Notice it's a little bit different. The only thing that's different from the last scenario is that we have a location column here, but we still have car classes. We have rent day, return day, demand, and forecasted price. Okay. But you can see here, I have my initial car inventory. Notice it's looking a little bit different. Notice I have to specify an initial inventory for each car class in each location here. So you can see here in Fredericksburg, I have 35, 85, and 90. Charlottesville, 15, 35, and 20. And then Arlington, 35, 35, and 50 here. Okay, and I'm specifying the locations here. And for the transfer costs, basically what I'm doing here is I'm making the transfer costs, I'm just setting those at $100 per transfer here. So it's a constant cost. Each transfer is going to be equal. If we wanted to, we could change this. We could have a specific transfer from one location to another for each car class. Okay, so what we're going to do, let me go back to the slides for 1 second. just want to pause and ask if there's any questions about this before we look at before we take a couple minutes and work through the coding exercises. Any questions, guys? Okay, so let's take a minute and we can certainly discuss as we go along, but what we need to do here is, you can see I've got a couple of to-dos, right? The first thing that we need to do is we need to add a dictionary for the t variable, okay? And it should be indexed over my car classes, location, and then the range 0, delta, up to delta -1. Okay, so just take a couple minutes, and by all means, feel free to discuss amongst yourselves how we do this. So as we get started, what we want to do, by the way, is come up to this previous case and look and see how we actually built our model. So this is where we actually build our model. So we can see here what we're doing is adding a component one at a time, right? And this is where we add our variable. This is where we create our variables here, right? So why don't we take, let's take 5 minutes and try to code a couple of these here, and we'll come back and talk a little bit about them.
Hi. So do we not have the Y and T in the complete version?
Say that
Because
one more time.
this to do for making the variable Y and the variable T, right? So do we not have this in the complete version of our code?
So yeah, the complete version is going to give you all the basically the solutions. All it is the constraints that we saw in the slides implemented here. But yeah,
Mhm.
so the y variable actually comes in a later, that comes in scenario three here. So we have we need here in this particular scenario though is the t variable.
Yeah, I pasted it according to the hint given there to do.
Okay. Yep. So pretty much what you want to do is just yeah uh, put in fill in and under the to-dos the constraints here and of course the components. So creating the variable t and then going in adding a component here, really just adding a subtraction piece inside the objective function and then going in here, adding constraint set 4 and 5 here. So let me take a second here and ask, so you guys had a couple of minutes to work through this. Was anybody able to solve this and to get to kind of see what the answer was here? So by the way, I think we talked a little bit about this at the beginning, but in addition to the learner notebook, you guys have also a copy of the complete, and the complete has all the constraints implemented. It's basically the completed workbooks. Now you'll find in all the scenarios in the learner notebook, you will find answers that are given, but of course they're not going to be correct until all the constraints are put in. Uh, so I'm going to bring up the complete notebook so we can kind of look and see. Go through here briefly. Okay, so what I did here, as we look at this in the complete notebook, this is going to show essentially the answers, if you will. You can see here, all I'm doing is creating a LP variable.dicts object here, a dictionary of T variables indexed over C, L, L, and then uh, the values 0 up to delta minus 1. Okay, and then add, go in and add, make sure that for constraints 4 and 5, sorry, which we had to also add. Also, we had to add the component to do that subtraction. If you guys remember, that was over 4 indices. So it's kind of a long sum. Okay, so we subtract this from the objective function. Okay, and then we have two constraints to implement. The first one is going to be the inventory flow balance, okay, which we implement like this. Again, this is kind of a long equation, a long expression here, so I just do it on multiple lines here. So we add to the model I is Hij equals Hij minus 1, and then we add up, we subtract out the transfers out from the previous night, add in the transfers 2 from the previous night, and the car is rented out on the current day, and the car is returned on the current day. Okay, and then we have to make sure that we don't transfer out more cars than are available at each location. Okay, we just sum over all days. Okay, and then in each location, and we basically, for each car class H and I, we just ensure that THI prime J, the sum of that is going to be less than or equal to IHI So which is our current inventory on day J. Okay. Questions, guys, about this scenario before we look at how we extend this a little bit to a more realistic case. Okay. So I'm going to move on to the third scenario. Let me bring up. Okay, in this third scenario, what we're going to do is we're going to think about how we do the transferring, right? So we're going to extend to use a little bit more realistic transfers. So again, when we talk about the capacity optimization part of revenue management, which is really the focus of today's discussion, the goal is how do we align our capacity intelligently? How do we use this as effectively as possible here? So if we think about transferring individual cars, one car at a time, having that kind of flexibility, on the one hand, that's really, really flexible. On the other hand, it's economically unfeasible for a number of reasons, right? One of these is, the notion of unlimited transfers just doesn't really work in the real world. Similarly, if you have a massive amount of cars that need to be moved, and it's one at a time, and you're not thinking about how you actually do that, if you're just imagining that that's a driver per car, I mean, that could be, tons and tons of people. You need an army of people to do that, which most rental car companies just don't have at their disposal. So in the real world, the way cars typically get moved from city to city. Now, I'll mention in some cases, some rental car companies will have more than one location in a given city, so it's just a short ways away, and they might move a couple cars here and there, back and forth. And those are done oftentimes by a driver literally just getting in the car and driving over, and then somebody else taking them back. But when we talk about going from city to city and moving large amounts of cars, again, that's not at all economically viable. So we use transfer trucks, kind of like what you see pictured here, to do this here. And so as we think about this, how does a truck work? Well, there's going to be, obviously, just like cars, there's going to be a fixed number of trucks that the rental car company owns. There's going to be a cost per trip, typically, which is, again, there's typically a homogeneous fleet of trucks. But the cost per truck is going to vary depending on how far they have to travel. So, it's going to vary between distance between locations. Another thing to think about is that each truck is going to have a certain capacity. How many cars can be mounted upon a truck here? So, we're going to say in this case here where we have a homogeneous fleet where each truck is going to be able to carry 8 cars at a time. Okay, and so when we model our policy, again, this is going to be something that varies from one company to another, one situation to another. What is your transportation policy? We're going to use a simple transportation policy, kind of like which reflects how we did it in the last scenario, which is each night a truck is going to make one trip from their current location to another location. So that's going to mean a truck starts at their current location and is going to be ending up at whatever location they transfer it to there. So they'll be there at that other location the next day. In reality, again, it can vary. There's any number of permutations. You can get into complex routing, where you have several stops in a night. That can sometimes happen here. Again, that just varies on, it's very particular to each individual circumstance, each individual company's circumstance here. So to illustrate the use of truck-based transfer, though, we're going to use a policy, simple transportation policy where it leaves a location at night, arrives, before the morning hours at the new location. The truck parks basically is now stationed at the new location here. But again, keep in mind, in reality, there's any number of ways, any number of different types of transportation policies that can be reflected in this. And whatever you come up with, that all has to be reflected in the modeling. So as we get into framing here, what we're going to do is we're going to modify our transfer cost parameter. So we're just going to let CI prime be the transfer cost per truck. So in this case here, the cost is not per individual car, but per truck. It's going to be the cost of, per truck from location I to I prime. Okay, and then just like before, we know that we have the inventory I variable and of course the initial inventory is a parameter for our cars. We're going to have a similar inventory variable for trucks. So we're going to let TI0 be my inventory capacity, my initial inventory of transport trucks at location I at the end of day J. Okay, and then we're going to have, again, some companies might have, larger trucks that can take on 12 cars, or some might have smaller that can take on 4. To generalize that, we're going to let KT be our capacity, how many cars can each transport truck carry. Okay, so we have a couple of decision variables that we have to add to this now as well to model the truck-based transfer. One of these is going to be modeling the number of trucks that are sent from one location to another. So we're going to let I prime J be the number of transport trucks that are sent from location I to I prime on night J. So remember, the day ends and there's the ending car inventory at the location. And then the night begins and then the trucks move at night, basically. And then they're stationed at their new location each day. Okay, and we're going to have the same inventory for cars. And then we're also, as we transfer cars, we have to have a decision variable that's going to tell us how many cars move from one location to another. But of course, in the new model, it's going to be constrained by the trucks. So to model the truck inventory, we're going to have TIJ, which is going to be the inventory of transport trucks at location I at the end of day J. Okay, so when we model this here, we have to modify our objective function. So we're going to modify it by revising the costs to reflect the cost of the trucks rather than the individual transfer costs of the cars here. Okay, and then we have to make sure, we have to revise constraint 5. If you guys remember constraint 5, we had to ensure before that at each, for each transfer, at each location, we don't transfer out more cars from that location than are found at that are found. So we include this here. We do this here for the trucks. Okay, and then for location 6, for constraint 6 here, what we have to do is we have to just develop a constraint that ensures the correct ending truck inventory on each day. And again, in this case, what we're gonna do is we're gonna assume a single trip per night, right? So what that means is, again, this is a simplified transportation policy. What that means is my truck leaves my location, it takes a set of cars over to the new location, and then it just stays there. And so it's available the next day, to transfer cars from that new location here. And again, this is something that changes, from one company to another, from one circumstance to another. Okay, and then we're going to have another constraint here. We have to make sure that the total cars transported from I to I prime does not exceed the capacity of trucks going on this route. Okay. So what I want you guys to do, I want to take a little breakout session. Again, I'm going to have you guys kind of think about modeling this constraint here. How do I ensure that when my truck goes out, I'm not sending more cars on a truck than can actually be carried here? How do I constrain that? My total cars transferred from one location to another doesn't exceed the capacity of trucks going on that route. So I want you guys to take a couple minutes. I'm going to have you guys, I want you guys not to do just the implementation in Python, but I want you guys to take a couple minutes and think about how to formulate this on paper. So let's say 5 to 10 minutes here. Let's say 5 minutes actually for time's sake. So at 12 let's say at 12:30 Eastern time, or I guess that's what 6:30 Central time here. Let's come back and think about and discuss how we might do that. But I see your hand is raised.
Yeah, so I think, I mean, it's kind of a flow problem. So how many trucks are going from any other node to this particular node that we want. So it's kind of like if we want the say for example it's a node K, and then we want to node that from each of the nodes that we have available, right? So facility location or the truck that are initially in that position. So we want to make sure that we want to calculate how many trucks are going from those locations to this particular node K. So that is a flow problem. So it's just so we calculate the flow of the trucks, and then I think for each, I mean, and then they might have been capacitated from before as well. So we need to take into consideration their remaining capacity, and then we need to given that we need to calculate like we need to put a constraint that the capacity of this truck going from here to here has this much capacity, and then we need to calculate how many cars can be transported that way. I do not have that in mathematical formulations, but I think that should be something like calculating the flow, and then um, uh, reducing the amount of cars that are already on the truck, and then just calculating how many trucks are going to that particular node.
Yep. That's exactly right. And you hit the nail on the head. This is really about the capacitation, the capacity constraints that we have here. So I'm just going to show this here. Uh, so, so first of all, we have as you mentioned, the flow. Again, two constraints. When we talk about adding the flow constraint, this is just like what we saw before for the cars. We have to have this now for the trucks. So my ending inventory is the previous day's ending truck inventory minus the trucks transferred out plus the trucks transferred in. So again, it's just like the cars essentially, right? But we have cars and we have trucks, and cars are loaded onto trucks here, but we have to maintain the inventory of both here, right? So we write it, again, this just mirrors, what we saw before in the very first simple car transfer constraint here. And actually, in the single location, we were just moving cars, from one day to another. So almost the same thing here in terms of its simplicity here. Okay, and then we also have to make sure that when I transfer my cars, just as you mentioned, Prajeet, I want to make sure that I don't send more cars than I have trucks, right? So if I have a truck, let's say I have two trucks, which is going to give me a total of 16 cars I can transfer. I don't send more than 16 cars out. Okay, and so the way I do this here is between every pair of locations, and this is exactly what you said, between every pair of locations I and I prime, over all days, or all nights, I should say, because the transfers happen at night, all nights 0 up to the last day -1, all nights from 0 up to the last night, I should say. We need to make sure that, the total cars transferred out across all car classes of a particular node. Again, so THII prime J is going to be the total number of cars of class H transferred from location I to location I prime on night J. That total has to be less than KT, which is my truck capacity, times the number of trucks transferring out. Okay, and this will make sure that I respect my capacity constraints here. This is going to make sure that I don't transfer more cars out than I actually have trucks going.
So I have additional question in that. So for this new constraint 7, we need to have each constraint, right? Because maybe there are some empty trucks in some days, some nights, right? And then it might it might satisfy this inequality, but there might be one more car on the truck one day, and then one less car on the truck another day, another night, sorry, and then that satisfies the inequality. So we have to put these inequalities separate, right? So is it some sort of matrix? Will it be in some sort of matrix form, or this is a single inequality?
So we just need this inequality here. This will make sure that the total cars. So again, this THII prime J is the number of cars of class H being sent from location I to location I prime on night J. That's what
Oh,
this
okay,
variable
okay,
means
that
here.
makes sense.
So to get the total
I
number of
have.
cars sent out from location I just sum across all car classes here. And of course, what that means is, that has to be less than or equal to the trucks going out.
Yeah, that makes perfect sense. I just thought G was multiplied or something. Yeah.
Yeah. Okay, so
I think we have a question on chat.
go
So it reads,
ahead.
Hi, I have a question related to Big M. If Big M has many rigs, is there any better way to write the constraint with Big M? And should we avoid using Big M?
Well, we actually, in this particular case, we don't need big M. So, as you can see here, we're not actually using it in this particular location or this particular set of constraints. But in general, big M allows us, we use this, if you remember, we used big M when we were looking at making substitutions, right? And in that context, when you're building for efficiency's sake for the solvers underneath the hood, again, we don't really look at this. We don't think about how the solving happens when we build our formulations here. But when we build our formulations, if you have a really large big M that can reduce the solver performance, that changes the relaxation, linear programming relaxation, and that can certainly impact the speed at which the solution happens here. And so generally, as a rule of thumb, when we use the big M, what we want to try to do is we want to try to find the smallest big M that's just big enough to guarantee that the logic to guarantee the logic of the constraints. Does that answer the question? Okay.
We do not have a response. So
Minor
okay.
delta here. I think the constraints right now don't forbid that we actually made this a multi-commodity flow, and I don't think you want that. So say I have locations A, B, and C. B doesn't have any Ferraris, but I'm moving Ferraris from B to C and from A to B. So the Kirchhoff constraints are good, right? What flows in flows out, but at the time the truck needs to leave, I don't have any Ferraris. So I would have to wait until the delivery from A goes up at B before I can send it to C.
Yes, and we had a constraint in the previous model. So for the cars, that's exactly right. To make sure that the cars don't leave, like you don't have cars leaving from a particular location more than you have the inventory. And that was a constraint that we had.
Okay, perfect. Good. Yep.
Yeah. Yes, we do have to make sure of that. You're absolutely right. Okay. So let's go ahead and take a second for the notebook. Actually, let me see here. I'm going to go to for time's sake, I'm going to skip the next breakout session because I can see here we're approaching the time, but I'm going to show a little bit in the notebook in terms of how we do this. Let me go here for a minute.
Can I ask one more question before that?
Sure, go right ahead.
Okay, so we do not have any distance constraint here, right? But if the truck has to flow from one node from like Melnov mentioned, like A to B to C, right? So I mean, and then the cost from going directly from A to C is more than going from A to B to C. So do we have some sort of addition to that problem or
Yes, and that you're absolutely right. And in reality, when you're talking about truck transfer where you have a homogeneous fleet, that's that's really one of the main things that impacts that, right? So we have so the way we do this here is the transportation, the way we're modeling a cost here is going to be the transfer cost per truck from location I to location I prime. So you notice what we're not doing again, if we had different classes of trucks, so for instance, a truck that could carry 12 would presumably require more fuel than a truck that is more weight, so it's going to require more fuel per distance amount, so that would need to change per truck. In this case, since we have a homogeneous fleet of trucks, we use, really the transfer cost is entirely based on the distance is how we're doing it, or based on between the two locations and not taking into account the truck. Does that make sense?
Yeah, it makes sense. So, if the cost from A to C is more than A to B to C, then this optimization solution would choose A to B to C, right?
Yep. Exactly,
Okay.
exactly.
Yeah.
So the costs are just, these are known ahead of time, or they're estimated ahead of time. There's always a little bit of variability to them, but typically they can be known with a pretty good degree of accuracy ahead of time, and exactly. And so,
But if cost is proportional to distance, then this will never happen, right? By the triangle inequality.
right, right, exactly. Just if it's reflecting reality, you're exactly right by the triangle inequality. Okay, let me take a second here. I'm going to show in the notebook. We'll go through the complete notebook just so you can kind of see the modeling. It really doesn't get that much different. No super exciting new things, as we progress from one scenario to now to another when we look at the actual code here. But it's just a matter of adding in some additional constraints here, those constraints that we looked at. So we have the same component here to read in the data from the raw data and produce the output, the inputs into the model here. And then we have our function, which builds the truck-based multi-location. But again, we just have the constraints. So you'll notice here, we have some of our, for instance, our trucking flow that we talked about. Here's our trucking flow that's implemented here. We also have our constraint here to make sure that the transfers don't exceed the capacity, just like we talked about here, that you guys actually worked out by hand in the last exercise here. So again, you can see how easy it is. Pulp doesn't even require a whole lot of explanation. You can see how easy it is and how simple how much it reflects just doing the math. So generally, once you can work out the math model on paper, it becomes very straightforward to transfer it into pulp here. Okay, as we finish up and look at our last scenario, I want to take a couple minutes and talk a little bit about this here. So let me just make a couple of additional remarks, just so you kind of understand the realism. I think I've hit on these already. But again, in this scenario, we're using still a very simple transportation policy where a truck leaves and it goes to another location and just remains there. In reality, maybe you might find a truck might visit multiple locations. You might find it needs to return to a station or maybe one of a fixed set of stations, fixed locations here. So there's, a lot of very company-specific logic that comes into this transportation policy. And you can see what it takes to integrate that into the decision making, the revenue management decision making, the capacity allocation. You have to build constraints. You have to have an appropriate set of variables and these kinds of things that take those decisions into account here. So every implementation for every different company is going to be a little bit different that involves these kinds of things here. I just want to mention that here. So even though we're getting to realistic transportation in this third scenario, it's still it will require additional tweaking, additional adjustment, to actually be used for a real company to model their transportation policy. Another policy that happened sometimes. Oh, go ahead.
Wouldn't it be a good idea then? I mean, before your model explodes in complexity, and at the end of the day, you're ending up with a suboptimal solution because you just can't handle the complexity. Wouldn't it be better to just use an approximation to the transportation costs? It's easy to compute.
That's another thing. Another common thing that's done is to use pre-computed routes. So you have basically what you're choosing from is a set of fixed routes.
Yes. Yeah. So that's one way, or just do them as an LP, as approximation for the cost. Yeah.
Exactly. It shortens it. Again, these kinds of models, we're going to see how these are used in practice in a second, or one way that they're used. There's a number of different ways. This is not the only approach to revenue management, by the way. This is a way. But yeah, when you get into using these models, they're repeated often. You have to resolve because conditions are constantly changing. It's actually a really good segue into our last scenario, which is if we look at what we've done so far, everything we've done so far really has been focused on a dynamic or a static situation, right? I give you a fixed demand forecast. I give you a fixed pricing, and your goal is just to figure out how to optimize against that, right? And that doesn't reflect reality at all. In practice, demand is constantly fluctuating. As I mentioned, the demand tends to be more accurate when you're looking in the near term, and it gets, it's more inaccurate as you get farther in the future. And of course, once you meet that near-term demand, all of a sudden, when you've actually done it and executed and sold the cars and they've come back, now you're at a different place in the horizon. That demand that seemed farther out and less accurate, it's become more accurate, and more stable. The same thing happens with pricing, though. As demand changes, and as circumstances change, pricing is constantly changing in revenue management. And so behind everything that we're doing, there's a demand forecasting engine. That's a big part of this, that's providing this inputs to us. And there's also, as I mentioned, a pricing engine, which is behind this, which is, producing appropriate prices for us, the best estimates for the pricing. But we haven't seen any fluctuating demand, right? So, which is what happens, and we haven't seen dynamic pricing integrated. So how do we do that in this case? So I want to mention here, there's a lot of ways, there's a lot of sophisticated approaches. This can get into stochastic optimization. One approach could be, with robust optimization. I don't know that that's used too much in practice. It tends to be a little bit conservative if you use robust optimization. But there's a number of different approaches that can be integrated to deal with this kind of uncertainty and this kind of fluctuating demand and pricing changes here. So, you can see here, for instance, as Taylor Swift makes a surprise visit in 2 days, that's going to impact the demand. As you have a big demand spike, that's also, a good reason to increase the price. And that can typically be done. The forecasts are more accurate in the near term. Another thing that we have to do, though, is as we make changes, we've already committed to some of, have sold some cars online, right? We can't just go to these customers and say, sorry, I'm taking all these cars away from you and giving them to somebody else, right? You have to incorporate that into the decision making as well here, right? Now, and this is per overbooking policy. So we haven't had any chance to talk about this. This is another component that we find in many types of revenue management. It's really, we see it more in the airlines. It works a little bit differently in the rental car, but the idea of overbooking is this. There's always going to be some cancellations, right? And so it's a pretty safe bet to sell a few more seats on an airline, for instance, than you actually are going to be able to meet, just knowing that there's going to be some cancellations. Now, sometimes it doesn't work out like you planned, and you sell maybe a couple more seats than you should have, and somebody winds up without their seat, and they can't go on that flight. And so then you have to give some kind of a compensation, give them a hotel room stay, be able to make the next flight and a ticket to the next flight, or some kind of, compensation like that. The other thing that you deal with the overbooking also is it can really make customers really upset with the company, and they promise they're never going to work with this company again. So it has to be done. There's immediately measurable impacts like the cost of sending somebody to a hotel. And then there's, the more intangible ones with estimating the impact of their anger and the frustration with you for overbooking. Also, I'll say ethics has to come into this as well. You have to think about, where is it, when is it ethical? We're going to talk about this. I want to make sure to include a little section on ethics about, with revenue management at the end of this here. But the idea is we have to honor reservations already sold. In this case, we're going to assume no overbooking policy where we don't do overbooking. So what this means is if I've sold some cars and the demand changes, I'm not going to go back and take those cars back. I'm going to assume that it's done here. So again, how do we incorporate changing prices, fluctuating demand, and making sure that as we, adjust our plan, we honor what's already been committed here? The way we're going to do this, again, as I mentioned, there's a lot of different approaches that could conceivably be applied. I'm going to use a simple approach, which can, which also, in actuality, tends to work well in practice. It doesn't require, understanding, characterizing, uncertainty statistically. It just reacts to uncertainty. And this is we're going to use what's called a rolling horizon approach, which is basically what we're going to do is we're going to resolve the model periodically at different times. And in reality, you might even do this multiple times a day. But, let's say, every other day we resolve the model. And so you can see here, my horizon is moving. My day one changes. If let's say I redo my modeling every day and resolve and adjust my plan every other day. I'm going to have a plan that starts on day one, and then I'm going to do it again on day three. I'm going to add a couple of days to the end of the horizon, and my day three becomes my day one in the new horizon. Okay, and so that we're going to solve like this here. But how do we do this? How do we ensure that we handle the commitments that we've already done? We're going to incorporate something called committed demand. So instead of just demand for each demand slot, each booking slot, we're going to have another column which is called committed demand. And these are basically the seats, these are the cars that we've already sold, the cars that we've already promised to our customers. Okay, and so what we're going to do, the way we do this, it turns out that the math is incredibly simple. The biggest difference here for us to handle this dynamicism is how we think about the solution, how we think about we use the model here. So we're going to add one more input, which is the DCK, which is the committed demand for slot K. Okay. And then when we go to do our modeling here, our constraint here that ensures we don't exceed our demand for each slot in terms of what we allocate, we're going to add a floor to that also, just simply ensuring that we whatever we allocate at least the committed demand to that slot here. And then this will allow us basically as the pricing changes, as the demand fluctuates, this will allow us to adjust our plan accordingly here. And again, if we have an overbooking policy, we can integrate that into the demands here that we sell. We can adjust the demand to reflect an overbooking amount for our demand slots here. Okay, I'm going to pause for a minute and just ask who has questions here. So this is how we can move from a static environment, relatively fixed model to this incorporating the dynamic pricing and the fluctuating demand. Who has questions about this?
On that, it's just a delta, but if you put a floor on every slot, you're not taking into account that you could upgrade somebody.
Well, you actually are, yeah. Because remember, what our model is implementing our substitution policy. So the total, notice here we're summing for this. If you look at the constraint here, what we're doing is when we're allocating not to exceed the demand as we had it before. If you just ignore the green part for a minute, we're summing over all the classes here.
Yep.
Okay? And if you remember, we have another constraint which is going to prevent allocation of a car class H to slot K if that's an invalid substitution.
Oh, I see. Okay, so you want the total capacity to exceed the okay, gotcha. Cool.
Yeah. Now, if our formulation, if our policy allows for substitution, then that will be, of course, reflected in the V variables. VHK is 1 if car class H is allowed to be allocated to slot K and 0 otherwise. And there's another constraint that makes sure that happens here. But this is just looking at the total allocation to each slot here. And this is just making sure that we can meet our commitments to our previous, the customers that we've already sold to. Okay, other questions, guys?
I had a question.
So we have 2 more questions on the chat. So by Adam, it reads, I always pick the rental one up from the cheapest, hoping to get an upgrade to maximize my rental value. How realistic are the numbers in the notebook? I'm wondering if this is a good strategy.
The numbers were generated from real data. I use enterprise car here based on where I'm at. I looked at some of the cities around here to get so I mean they're not real data, but they're simulated from realistic data is what they are. That's a good question. I think that every company is going to have slight differences in terms of how it does its upgrade policy. I don't know that every company is going to allow an upgrade from from a compact to a luxury. Maybe, but most likely I would imagine most of them would do it from a mid-size to a compact. They would allow that kind of an upgrade. Yeah, that's really a hard question to say. I'm not sure that you can really come up with a clear strategy, from this modeling. But if the upgrades are allowed, it just depends. What's going to tell you whether or not you're going to get an upgrade is going to be, do they have higher demand for the lower class car in general? If they have a higher demand than they can satisfy with the lower class cars, then you're going to start to see the upgrades being moved to meet the demand for those cars.
Yeah, so my thinking is the optimal solution would actually be fractions of a car, because we have to do whole numbers.
Yep.
And you're going to have the most at the bottom. Yep. So the one tier up, you're going to have a little bit smaller inventory. So you'll hit that barrier to an upgrade sooner. That's what I was thinking when I've been doing this strategy, and it seemed to work out pretty well.
Yeah. Interesting. I've never thought about gaming the system. Maybe that could be an interesting problem to work on. Seeing how you can get a free upgrade.
Well,
great to get a Ferrari.
If they offer you an upgrade for a cool price, chances are they have to upgrade you anyway, so you should always decline that.
That's probably true, actually. That's probably true. This is another thing.
Yeah, that actually has happened to me when I've gone and they're like, would you like to upgrade to a SUV? And I'm all, no, thanks. And they're all, well, here's an upgrade to an SUV for free.
You've discovered exactly what they're trying to do here. Yes, and anytime an upgrade is made, that's probably what they're probably always going to ask before they offer it, just like that. Indeed. Good question, though. Yes,
I had a question. Can I ask a question?
absolutely.
Yeah, so I was a little late to the presentation, so I'm kind of a little lost. But this committed demand,
Mhm.
is this coming from like, are you doing a forecast and then you're just assuming that it's true, and then you allocate like for the next slot that's committed demand, how do you?
Close.
Okay,
So the demand that we're working with, that's a great question. And let me make the distinction between forecasted demand and committed demand, right? So the demand that we've been working with is actually the forecasted demand. So
okay.
again, what we're doing to incorporate changing prices and changing forecasts for the demands, we're resolving the model periodically. We're frequently resolving. We're basically what we're doing is we're adjusting our plan as we go along and
With
making it
updated
more reflect the output.
forecasts, is it with
Yes,
updated
exactly. The
forecasts?
forecasts are changing and
Like more
becoming more
accurate
accurate
forecasts? Yeah.
as we go forward. When we look at the short term, the nearer term is always going to be more accurate in
Yeah.
general. But at the same time, because we're solving this periodically, right? As we solve at some point in the future, and we made some allocations at one point in time in the past, and we sold some of those seats, some of those cars according to our plan. We've promised these cars now to our customers.
Okay,
So
so
we
you
have to
know
we
that
have to make
they're
sure that we incorporate that into the decision making as well. And that's what the committed demand is. The committed demand is those cars that we've already sold in a previous iteration of the plan.
okay, so it's like if I go on the web and I'm booking in the future and like I pay for it, so that's it's like already solidified that this is true demand. Or it's not, it's a sales, like done
Yes.
true.
It's
Okay.
done sales. That's exactly what it is. The committed demand is done sales.
Okay, and
Yep.
then you're rolling because, yeah, I guess this is another question is that like sometimes I have the tendency to hear all these terms of like stochastic, robust optimization, and I kind of think to myself, oh, that's what I should be heading towards instead of doing like this really simple stuff because I'm used to like rolling because it just makes sense. We get better forecasts. Um, is this more common in the industry to do this? Or should I try to stop doing this like, oh, I should do robust optimization or stochastic? Because I keep thinking to myself that if I don't do that, then I'm not really being good at this. So it's just like hard for me to know because I don't know what the industry standards are.
That's a great question. It just varies, from context to context. It's always good to know the different capabilities out there, the different approaches to this. They are more sophisticated. I'll certainly tell you that. It takes a little bit of learning to look at robust optimization, to look at stochastic optimization, some things to learn. But what industry I'll tell you cares about is, ability to implement and to do well in practice. So even exact optimization in most, not just in revenue management, but in lots of different kinds of industry problems. When you look at vehicle routing, when you look at anything, the goal is not necessarily to get the exact optimal, but to get something that can be automated well and that can be integrated into the business process as well, and that produces good results. And of course, you get something that works good, and then you iterate on that, you improve it slowly. So maybe a company might start with an approach like this and get it into practice, and then they might say, hey, what if we tried stochastic programming with this, stochastic optimization in this? Can we try this out and see how it would work compared to what we do? So you get a baseline working that works well, and then you iterate, make small improvements like that. And that's where a lot of this will come into, but it certainly can't hurt to go and learn these things. But there's a lot you can do without it. I'll say that.
Okay, cool, thanks.
But the uncertainty is one of the things with, using optimization in the real world, you have to get used to uncertainty and you have to get used to changing conditions. It almost never works to be able to generate a static plan like we do in the classroom. Professors, we teach this. I do it too. We work through the modeling. I try to teach the thinking behind the modeling, but that's necessary, but it's not sufficient for the real world. The real world is
Yeah,
characterized by change and constant need to update plans and
yeah.
deal with uncertainty.
Yeah. When you say this word policy, because you said it a couple times, and I only crossed this word like in one context, and it's like SDA, sequential decision analytics. You don't mean policy in that framework, right?
No, I just mean what's allowed. So I used it, for how we do our transportation. In other words, what's allowed with transportation moves. I also used it in the context of substitutions.
Okay.
So what's allowed with substitutions? So one substitution policy might be I allow a higher class to be substituted for a lower class.
Ah, okay, okay, I get it.
Or,
Thanks.
another one might be I allow one class up. I don't allow a luxury to go down to a compact, but I allow a luxury
Okay,
to a midsize and a midsize to that's another
so it's
policy.
like a
So
rule.
that's all I mean by policy. That's kind of what I'm using here.
Oh, okay, perfect. Thanks.
As we finish, guys, I want to take just a minute to talk a little bit about ethics and revenue management because this is one of those areas, one of those applications of operations research that it needs a little bit of thinking in terms of how we actually apply it. And it can be used in genuinely unethical ways. So one of the things, just to be mindful of, I say this to you guys as a group because I know there's some very, very smart, very capable people in this group. Some of you have companies. Some of you are able to take what we just learned, this little bit, and run with it and actually roll off a new product that can really help a company increase its revenues. And so, I just want you, as you take these things that we've talked about today and maybe start to use them, just be mindful of a couple things, right? So one of the things you don't want to do, or you just want to be mindful of, is exploiting through unjustly high costs for essential services, right? So when we're talking about rental cars, people use those when they go on vacation, and yes, it would be nice to get a luxury car. Maybe that's out of your price range, but if you can't get a luxury car, even you can't get a compact car on a particular day, that's not going to destroy your life if you think about it, right? But what about if we talk about some other things that are necessary for survival, right? What if we shut some groups in the name of profit out of access to goods or services that are necessary for survival? So I'm talking about things like maybe medical care or housing or these kinds of things. This is where you have to think about the ethical implications a little bit more here. Another way that revenue management can be used is industry collusion, leading to monopolistic exploitation. So here in the U.S., I have a link here in the slides, but there was a lawsuit that just went through a company called RealPage, which does this for short-term rentals. And basically, they were, all the landlords were using this tool, and all the prices were pooled. It was basically all the landlords, instead of competing against each other, were functioning as one collective monopoly. So, again, when that happens, you force people out of houses. Huge swaths of houses apparently were being kept. They could have been rented out to people who needed them, but they were just being kept off the market to raise prices. So again, you have to think about the impact of things that you're doing. Also, the appearance of unfairness. This is something, again, revenue management, uses price discrimination. That's a part and parcel of what you do in revenue management. You charge some prices to one segment, the same exact product essentially. The seat next to one person pays $200 for a seat, and then the person next to him pays $3,300. Huge difference. Questions can be asked, right? Why did that person only pay this amount, whereas I had to pay that amount? And again, this is not necessarily unethical, but this happens when customers can't perceive a reason for the price differences here. And when you have this, the pricing appears arbitrary and exploitative. And if without some transparency, this can cause customer resentment and can cause churn here. So this is just something to be mindful of. As we talk about using revenue management in an ethical way, there's a couple of questions just to kind of think through, right? One of the first ones I would encourage you to think through if you're thinking about building an RM platform is, am I dealing with goods or services necessary for survival? And is there the possibility of shutting people out of something that's essential for their survival altogether, just in the name of profit here? Profit's important for sure, but there's other things that are more important. And so we have to think about these. We have to ask those questions, right? Another thing that can be helpful is just to think about is, can you help make the rationale for price distinctions? Can you help make that clearer to the customers? Is there a clearly perceived reason for this? Does the price differences enabling me to serve different segments, for example? A great example of this is the airlines. This is a good example of the ethical revenue management, right? Air travel is not really necessary to survival. At the same time, if airlines sold all their seats, allowed all their seats to be sold for $200 at 6 months in advance, they all book up, and that business flyer who needs to go make the $20 million deal across the country all of a sudden can't get over there because there's no seat available here. So you can see here, this actually does good. This does social good by, having this price discrimination, making sure that you're having some capacity available for this other business segment as well here. So again, you can kind of see, you want to be thinking about this as well. Think about how you're going to be applying revenue management, making sure that you're not going to exploit, those and shut them out of things that are necessary for survival, and also try to enable the price discrimination, enable the rationale for that to be made a little bit more transparent here. And so the bottom line, I'd say, it's been said before, you don't want to try to gain the world, and forfeit your soul. When you do business profits, it's certainly very important in business, but it's not worth, it's not should not come at the expense of causing harm. Um, okay, so in terms of our discussion on revenue management, that's it. There's a lot more that we could cover. There's a lot more to be covered, I should say. We've barely just scratched the surface, but this gives you a little bit of a sense as to what it's all about. And I just want to turn it over now. We're a little over time, so anybody can leave. But if there's any questions or further discussion, I'd just like to open it up. Anybody?
Uh, we had one question in the chat
Can you
from
read it?
Gole. Yeah,
Sure.
it rates how effective is stochastic optimization in scenario 4?
I mean, that's a good question. In these scenarios, I didn't really I didn't try out any other approach than the approach that we looked at. Um, the best bet, is kind of like what I mentioned, how this would be done in practice. You would start with some kind of a baseline. And typically when you start with a baseline approach, it's a simpler approach. And the rolling horizon is a very simple approach that we can use. It's flexible, doesn't require distributions, understanding of distributions. And then you can incorporate stochastic optimization, and you can try out a stochastic formulation and see if you can increase the results. But I guess the answer to your question is I'm not quite sure.
Yep. So I do have one question. So since you have this problem, I think you took the data from the real world, right? And then so you have previously implemented this model somewhere. So, given how random and there might be a random noise in the price engine and demand prediction, demand forecasting, how has this model fared in real world settings? Because the price can be it can be random, demand can be random. So,
Yep.
uh,
So in terms of the real world, yeah, I mean, this model, by the way, this has not been implemented. This model was created for this particular scenario based, again, yeah, the data it was generated from real world data. I use that as a starting point. Again, but this model has not been implemented. We have a number of simplifications in this model, as I mentioned, like especially the transportation, how we do the transportation. We had a very simplistic transportation policy used here. So, in a nutshell, I can't really say exactly. But one of the things, if we go back to, what we saw, I'll just bring up the notebook for a minute. I'm going to go back to the comparison that you can kind of see. So we did a simulation to kind of see how this does. And this was the very simple scenario, the single location scenario, right? So if we compare this, if we compare using revenue management to not revenue management, right? If we compare this to a first come, first served, which is you have a software system, a computer, a website where customers go, and as soon as they book something, it just finds the first one of they book for a slot and just grabs a car and allocates to that slot, and without thinking about how that might impact its ability to serve other slots. So literally just a first come, first serve. Again, we did 20 iterations, 20 simulated iterations, and you can kind of see where these pan out, right? If you don't use revenue management. If you use the optimal capacity allocation that we did, some modeling though, you can see sorry, I'm moving something out of the way. You can see a big difference here. We go from, the 50s up into the low 80s for no upgrades, up into the upper 80s when you allow for upgrades here. So you can see, especially in these cases where you have a lot of tricky ways to allocate, an innumerable number of possibilities of how you can allocate. The optimization makes a big difference in this here. And of course, what I'll say too is, you can see the way that we're doing this here in these scenarios. We are going against a forecast demand that tells you that the quality of forecast is also very important. Now, of course, we're able to adjust accordingly, right? As the forecast becomes more accurate in the near term, we adjust to that, we resolve, and it will produce good results. But again, even if in the near term that is not good, we're going to have problems, right? No matter how good our optimization is, if we're not optimizing against something that approximates reality, again, a forecast isn't going to give us reality, but it's going to approximate reality. No matter how well that happens, though, we're not going to be able to get a good result like that. So forecasting is very important. And also the dynamic pricing aspect here, continuously adjusting price based on what the market will tolerate.
So basically, the expected value, like, over the long iterations of these things, the expected value turns out to be much better than what we have as the, uh, go-to method, like first come, first served, or something like that, right?
Exactly. Yes. The expected value, revenue management will deliver a substantial amount of value over the long term.
Okay. Yep. That's it. Thank you. I do not think we have any more questions, so I'm just going to stop the recording now. Thank you so much for doing this session. It was really interactive and I got to learn a lot. I'm sure it's the same for everyone else here. Thank you so much.
Thank you
Thanks.
guys for